section 1.3 of the notes: absolute value, bounds, and intervals. Okay, so the absolute value is a function that we introduced in order to measure how big or small a real number is. Okay, so in order to deal with that, so if we have, for instance, 3 and minus 3, if you think about it, okay, you have the real line 1, 2, 3, and minus 1, minus 2, minus 3. Well, it seems that 3 and minus 3 are kind of equally large, right? It's not that, well, 3 is greater than minus 3 in the sense of that it's more positive, but if you think about, the distance from 0, it's kind of the same. Okay, so this is what the absolute value wants to measure. Okay, so the absolute value for any x, a real number, we define its absolute value as, and we write it like this with these vertical bars: x is the maximum of x and minus x, which means that the absolute value is going to be x if x is greater than 0, and minus x if x is smaller than 0. Okay, so the absolute value of minus 3 is 3, as it is the absolute value of 3. Okay, so the same value. So there are some important properties of the absolute value. The first one is that the absolute value of x is greater or equal than 0. This is very easy to prove. Now, this is equal to 0, the absolute value of x is equal to 0 if and only if x is equal to 0. And this if and only if, I don't know if we have seen it before, but this means that the two directions are true. If x equals 0, then the absolute value of x is 0, and the other way around. If the absolute value of x is equal to 0, then x is 0. Okay, that's what if and only if means. Okay, it's important that you remember this. The absolute value of the product is the product of the absolute values, and then the absolute value of the sum is smaller or equal than the sum of the absolute values. Okay, these are very easy to check. And then the final property is that the absolute value of the difference of the absolute values is smaller than the difference, so the absolute value of the difference. Okay, so how do we prove this? Let me prove this one for you. Okay, so the absolute value of the difference of the absolute values is smaller than the difference of the absolute values of the difference. Sorry. So let me think. You can think of the absolute value of x as this: x minus y plus y, right? Because we are summing and subtracting the same number, so this is just 0. Okay, and this we apply property 4, and this is just smaller or equal than x minus y plus y, right? And so if we subtract the absolute value of y in both sides, we have the absolute value of x minus the absolute value of y. It's smaller than the absolute value of x minus y. But we can do the same thing with y. So y minus x plus x is smaller than y minus x plus x. But this is the same thing as y minus x. Okay, I'm subtracting x in both sides. And then this is smaller than, but the absolute value of 1 minus x is the same as the absolute value of x minus y, because the absolute value of x is the same as the absolute value of minus x. Okay, so that means that x minus y is smaller than this, y minus x is smaller than this. So if x minus y is smaller than 0, then the absolute value of this, well, the absolute value of this, if x minus y is smaller than 0 is going to be this, but this is smaller than this. And if x minus y is greater or equal than 0, then this thing is going to be like this, which is also smaller than this. Okay, so we have proven this, these two parts. Okay, now bounds, this the second part of this lecture. So suppose, or let A be a non-empty subset of R, and we write it like this: A is a subset, and then this kind of weird C means this is a subset. Okay, and let X be a real number. Okay, so X is an upper bound of A, of this set, if X is greater or equal than A for all elements of A. Okay, so suppose that we have A is 1, 2, 5. Okay, well then if X equals 7, then 7 is an upper bound of A. Okay, because for all numbers in A, X is greater than them. Okay, and also if X was 5, 5 is also an upper bound because it's greater or equal than every element in A. Okay, so that means that A is bounded from above, we say. And similarly, X is a lower bound of A if X is smaller or equal than A for all elements in A. Okay, so for instance, in this case, X equals 0 is a lower bound, or minus 1 or 1. All of them are lower bounds for A. Okay, so a bounded set so A is bounded if it's bounded from above and below at the same time. A bounded set has many upper bounds and many lower bounds. Okay, now we say that X is the supremum of A if it's its least upper bound. Okay, so well, and if A is not bounded from above, we say that the supremum of A is infinity. Okay, so in this case the supremum of A is 5. Okay, because from all the upper bounds that we can find, the smallest one, okay, the least one, is 5. Okay, and X is the infimum of A, inf A, if it's the greatest lower bound. And if A is not bounded from below, we say that the infimum of A is minus infinity. And here, the infimum is, so this is the supremum, the infimum of A is 1. Because from all the lower bounds that you can think of, the greatest one is 1. Okay? Now, if the supremum of A belongs to A, then we say it's the maximum. Okay, so in this case, the supremum and also the maximum. And the same with if the infimum of A belongs to the set, it's called the minimum. Okay, so in this case, it's not maybe not very interesting, but if you think about this set, for instance, let's see, 1 over n for n natural numbers. Okay, so we have seen this before. A is the set, okay, curly brackets, of all numbers that have this form, 1 over n, where n is a natural number. Okay, so it will be 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on and so forth. Okay, well, in this case, 0, this set is bounded from above by 1. Okay, so, and the supremum of A is 1. Okay, because there's no smallest number that is greater than all the numbers in A, but not smaller than them. And also it belongs to A, so it's also the maximum. Now the infimum of A, you can think about it for a minute, but the infimum is 0. Okay, so every negative number is a lower bound for A, but the infimum, the greatest of them, is 0. Okay, any positive number, doesn't matter how small it is, there's an n so large that it will be smaller than that positive number. Okay, so the infimum is 0, but 0 does not belong to A, so 0 is not the minimum of A. Okay, because there's no non-number n such that 1 over n is 0. Okay, you could say 1 over infinity, but infinity is not a number. Okay, infinity is not a number in the natural numbers. So that's kind of an example. But then we will have some exercises to get you familiar with this. Okay. So let's see. Next step, completeness theorem. Okay. So in the previous lecture I talked a bit about the real numbers, but some of the properties they have, and in the lecture, in the notes, you have more details about that. And if you were students in a math degree, you would have gotten to the reals or defined the reals in a rigorous sense, and so that you would have seen that the reals have a very important property that's called completeness. The reals are complete. Okay, and there are many ways to kind of reach that property, but one of them is to use this what we call the completeness theorem, kind of similar to this complete action, if you want. Okay, so that's not important. Just that kind of the nerdy background of this, but you know, the real numbers have a very important property, is that they are complete. Okay, and this property can be expressed in this theorem. Okay, this theorem is the completeness theorem, and it says that suppose A is not a subset of R. Okay, just like before, A subset of R, and let it be non-empty. So A has some elements. Okay, this is the empty set. So the empty set would be the set that doesn't have any element. Okay. Well, so A has at least one element. Well, then these two properties are true. The first one is the supremum property. If A is bounded from above, then it has a supremum. And the infimum is properties that if A is bounded from below, then it has an infimum. Okay? So for instance, if we have the set A is the set of all real numbers such that x squared is smaller than 3. Okay? So if you think about the function x squared, okay, so this is A is the set of all real numbers such that the x squared, the value squared of x, is smaller than 3. Okay, so if you paint the parabola x squared, that, and this is 1, 2, 3, then A is the set of all numbers that lie in here. Okay, excluding this, which would be the square root of 3 and minus the square root of 3. Okay, so you could rewrite this like this: x in R such that x is greater than minus square root of 3 and smaller than square root of 3. Okay, and there's no smaller, greater, equal than, or smaller, equal than, because square root of 3 and minus square root of 3 do not fulfill this property. Okay, so the upper bound, so you can think of, upper bounds for this are 10, 100, whatever. But square root of 3 is an upper bound of A, and actually this is the supremum of A, because there can be no smaller bound. If you think about it, if you pick any number that's just smaller than the square root of 3, then it fulfills this condition, and that number will belong to A. But this number is the smallest of the upper bounds that is greater than every other element of A. Okay, but it doesn't belong to A, so this is not the maximum of A. And with the same argument, we can say that the minus square root of 3 is the infimum, and it's not the minimum of A. Okay. So yeah, and then finally in this lecture, intervals. Okay, so the following subsets of R are globally referred to as intervals, and you have seen this before, so I hope this is not a surprise. An open interval, and we call it with this open brackets a, b, is the set of all real numbers x belonging to R such that x, the numbers that belong to this interval, are between a and b, but a and b are not included. Okay? A closed interval is the same as before, but a and b are not now included. So it's the same so x is greater or equal than a and smaller or equal than b. Semi-open intervals are the same, are open, closed, and closed, open. So here a is not included, b is included, a is included, b is not included. And then finally, infinite intervals from minus infinity to b closed, so the set of all real numbers that are smaller or equal than b. Minus infinity to b open, real numbers such that x is smaller than b, so b is not included. The same with closed to infinity, open to infinity, and infinite intervals from minus infinity to infinity is the same as R. Okay? So consider this set. A is the set of all real numbers such that the absolute value of x is smaller or equal than 4. Okay? So which numbers do belong to A? Well, suppose now that x is greater than 0. If x is greater or equal than 0, then the absolute value of x is smaller than 4. So this is like this. Okay, this is true. When x is greater or equal than 0, then the absolute value of x is x. And then so we can rewrite this like this. So this includes all numbers that are greater than 0 and smaller than 4. And we say this is from 0 to 4 closed. Okay, so let's call it a sub 1. And b, if we assume that x is smaller than 0, then the absolute value of x will be minus x, and so this is minus x is smaller than 4, or in other words, x is greater or equal than minus 4. So x is smaller than 0 and greater or equal than minus 4. This would be minus 4, 0, open. Okay, and we call it A2. Now A is the union of these two sets, because this is for x in R, so we separated x in R in two cases that when you join them, you have the whole of R. So this is, okay, and this is the union of two sets. Okay, so A is the sum of these two sets. So we have minus 4, 0, open, and the union from 0 to 4. And you can see that this is minus 4 to 4. Okay, and you can apply the definitions to see why this is true. Okay, this includes all numbers that are greater or equal than minus 4 and smaller than 0, and this includes all numbers that are greater or equal than 0 and smaller than 4. So if you join these two things together, you will have all numbers that are between minus 4 and 4, with 4 included. Okay, and then another example. We have set B, so real numbers such that x minus 1 times x minus 2 times x minus 3 is negative. Okay, smaller than 0. So which numbers belong to this? Well, if you think about this, as you go from x equals, from minus infinity to infinity, you have three products here. And in order for this to be negative, you have either this is positive, or these things are negative, or this is negative and this guy, well, no, sorry, this is not true. Either all of them are negative, okay, negative times negative is negative, or this is negative and these two guys are positive, this is positive and these two guys are sorry, this is negative and these two guys are positive, and this is positive and this is negative. Okay, 4 cases. So in the first one, so it's either x minus 1 is 0, smaller than 0, x minus 2 is smaller than 0, and x minus 3 is smaller than 0. Okay, if we have the three conditions together, we realize that this implies x minus 3 is smaller than 0. Okay, so in this case, for this case to be true, we have b sub 1 is the open interval from, well, this is x is smaller than 3, right? So um, sorry, yeah, I made a mistake. So again, it's not x minus 3, x minus 1, okay? Because the only condition that fulfills the three inequations is that x is smaller than 1, okay? If x is smaller than 1, then it will be, this will be true and this will be true, but not the other way around, okay? So this one is the open interval from minus infinity to 1, okay? All these sets will be negative. Now, let me see. We have x minus 1 is negative, x minus 2 is positive, x minus 3 is positive, okay? So actually that means that, you know, x is smaller than 1, but x is greater than 2, which is, and x is greater than 3, which is impossible. So this is not, you cannot have that, okay? There's no way you can have this property. Now, if x minus 1 is greater than 0, x minus 2 is smaller than 0, and x minus 3 is greater than 0, then you would have x minus smaller than 2, but x is greater than 3. So then again, it's impossible to have this property. And now finally, that x minus 1 is positive, x minus 1 is positive, and this is negative. So x is greater than 1, x is greater than 2, but x is smaller than 3. Okay? So if you put these two properties together, then that means that x has to be between 2 and 3, right? So that means this is B2, open interval from 2 and 3. And B is the union of these two sets. So that means it's the union of these two intervals. Okay? So if you try to think about any other number outside these intervals, you will see that this product is non-negative. Okay, so it's either 0 or positive. Okay, so that's the end of this lecture, and this is the end of the unit, the first unit.